Start from current slide. All right, good deal. Any questions on anything we've done up till now? Now, this is the last section in Chapter 2 that deals strictly with polynomial functions. And this is the one that sort of ties a lot of things together. You remember early on we talked about what end behavior of polynomial graphs look like, going up or down, right or left, whichever it is, always going to an infinity. We talked about other features of it, how many changes of direction, how many zeros, those kinds of things. In this section, we're going to focus on finding those zeros of the polynomial functions. And that's what we're all about here, okay? Now, if you got a quadratic, factor it, or use a quadratic formula. But for the higher level, hey, it gets a lot harder. Here is the one test that I think is going to help you more than any other single test to find those zeros of a polynomial function. Now, it only will find the rational zeros. It will not find irrational zeros. It will not find complex zeros. But at least it gives you some zeros that you can start finding, and then usually you can come up with the rest of them, or most of the rest of them anyway. Okay, so here we go. No questions before we get started. The rational zero test relates to the possible rational zeros. Now, what do we mean by rational zeros? Does it make sense? No, that's not what we're talking about. Not quite. Rational? What's the first 5 letters of rational? Ratio. What does that mean for you? Say again? Ratio of two numbers is division. It's a fractional form. Okay? The rational zeros of a polynomial function. Now, these polynomial functions we're dealing with now have to have integral coefficients. Okay? Now, they can be positive or negative, but they've got to be whole numbers. You can't have any with fractional coefficients. You can't have any with radical coefficients. You can't have any with complex coefficients. You have to have integral coefficients. But most of our polynomials have that, and it relates the rational zeros of a polynomial to the leading coefficient. Remember, that's your a sub n, the first coefficient you have, and the constant term, which is the last term that you have when written in decreasing order of the powers. Okay? And here's how it goes. Rational zeros test if the polynomial function f of x, okay, a sub n, x to the nth power, remember this is just a coefficient, and the only thing this n is doing is identifying is the coefficient that goes with x raised to the nth power. This is just a marker. That's actually part of the problem, okay? Plus a sub n minus 1 times x to the n minus 1. See, these match. This is part of the exponent, this is part of the problem. This just says this is the coefficient that goes to the exponent. Then you count all the way down until you get to a sub 2, x squared, a sub 1, x to the first power, plus a sub 0 times x to the 0th power. X to the 0 is 1, so that's just a sub 0. Okay? Now, if this polynomial function, like this, okay, has integral coefficients, every one of these a's is an integer. Could be positive or negative, but none of them are fractions, none of them are decimals, none of them are radicals, none of them are complex, having an imaginary component to them, okay? As long as these are all integers, you're fine. Then every rational zero of this function, every one of them is going to be of the form p over q. Well, yeah, that's a ratio. That's not saying a lot, but until you get to the next part, where p and q have no common factors other than 1. So in other words, if this was a 12 here, and this was a 4 there, you have a common coefficient, common factor. Get rid of those, and Kaylee's here. Okay. Got to find you now. There you are. Okay. So they have no common factors other than 1, and the p's here are a factor of the constant term a sub 0. Okay? Constant term a sub 0. And q is a factor of the leading coefficient a sub n. Okay? We have just narrowed it down big time. Still may have a lot, but you have narrowed it down greatly. Okay? Now this is a lot of blah, blah, blah so far. Let's do a little bit more. Okay? To use this rational zeros test, you should first list all the rational numbers whose numerators are factors of the constant term, whose denominators are factors of the leading coefficient. Factors of the constant term on top, and all the factors of the leading coefficient on the bottom. Having formed this list of possible rational zeros, then use trial and error. Okay, we remember that from our factoring. That was one method we used. Now we're going to use another trial and error method to determine which, if any, are actual zeros of that polynomial. And you'll find out this is a little easier than it sounds like. Note that when the leading coefficient is 1, this one right here, leading coefficient in the denominator, if that's 1, remember those are always the easiest to factor. They're also the easiest to find here because the only factors of 1 are plus or minus 1, right? So that's going to make the whatever your factors of the numerator are, the constant term, they'll be the only possible factors, okay? The possible rational zeros are simply the factors of the numerator, which is the constant term, okay? All right, let's do one, okay? Now, to begin with, they seem a little magical. After a while, you'll say, oh, wow, this really works nicely. Find the rational zeros of f of x is equal to x to the fourth minus x cubed plus x squared minus 3x minus 6. Okay? Wow. 5 terms. You can't even use factoring by grouping. We would be in serious trouble if we didn't have some technique to come up with the possible rational zeros of that polynomial. So what's the rule say? All your possible rational zeros are going to be of the form P over Q, where P is all the possible factors of what? The constant term. And what is your constant term? Negative 6. So all the possible factors of that, and remember, use all your signs. They can be plus or minus. What's the possible factor of 6? Say again?
2 and 3.
2 and 3, but don't forget 1, plus or minus 2, plus or minus 3, and 6. Okay? And over your denominator, which are all the possible factors of your leading coefficient, which is 1, so that's just plus or minus 1. Well, guess what? That doesn't contribute anything new. We know what the possible rational zeros are. Of all the numbers that exist, we're down to 8. Plus or minus 1, plus or minus 2, plus or minus 3, or plus or minus 6. That's all, folks. That's all we have to investigate. I'll write them out. Plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Okay, now, which of those you think that would be the easiest to try to figure out if it's a 0? Second?
1, 6.
Okay, the easiest would be 1. Okay? Because to find a 0, if x is a 0, when you plug in 1, you should get 0, right? And what happens if you plug in 1 here? What's 1 to the 4th power? 1 minus 1 to the 3rd power. 1 plus 1 to the 2nd power. Minus 3 times 1. Negative 3. Minus 6. Minus 6. Ah, you just add the coefficients, isn't it? So here's minus 9, minus 10, plus 2. That's not going to be a 1. Not going to come out being a 0. Okay? That's the easiest one to do for plus. And guess what? That's always an option. So try it first. It doesn't work. So let's go to the next one. What you want to try next? We eliminated plus 1 just by a simple substitution. Okay? Now the rest of them we're going to do something else. But 1 is so easy. So negative 1. Okay, now, in my mind, the easiest way to do this is synthetic division. Put a minus 1 on the outside, and you have to remind me, what do you put on the inside? I can't hear you. I can't hear you. Yeah, the leading coefficient, which is 1. Say again. Minus 1. 1. Negative 3. Negative 6. Okay? Do we have enough numbers there? What's the degree of our function? 4. How many numbers we got? 5. You need 1 more than what you got, and that's what we got. Sure enough. Okay. Brianna's here. Okay. And Melva's here. All right, good deal. Anyone else come in since it's called off? Okay. So yeah, and the other thing, the 2 things you have to watch for when you're doing synthetic division, absolutely necessary, be sure you've got the polynomial in decreasing order of powers. And we do. 4, 3, 2, 1, 0, blast off. Okay? And the other thing we've got is we're not missing any terms. I didn't skip any of the exponents there. And we checked that when we counted the numbers. 5 here, 4 there, that's perfect. Okay? Now, what's our next step? Skip a line, draw a line. That's my little rule. The book never uses it. And then you do what? Bring down the 1. Multiply, and you get negative 1. Then add, and you get negative 2. Then you get 2. You add, and you get 3. Say again. 3. Okay, thought so. Okay, then you get negative 3. Then you add, and you get second negative 6. Is that what you said? Okay. And then you get 6. And look at that. Add, and you get 0. Ding, ding, ding. We found a 0 for this polynomial. X equal negative 1. Okay? Find all the rational zeros. We got 1. X equal negative 1. Now, remind me, how many might we find? What's the maximum number of zeros that polynomial could have? 4. 3 turning points, 4 zeros. We may not find 4, but that's the maximum we can find. We found 1, ready to keep going, right? Now, here's a little thing to remember. Since this is a 0 of this one, then the 0 of the bigger one will also need to be a 0 of this reduced polynomial as well. So don't go start back up here, use this one. Okay? Now, second thing to remember, if plus 1 didn't go in this one, it's sure not going to go in that one either. Okay? So don't bother with plus 1. But you still need to try minus 1 again because you may have multiple zeros. So let's try minus 1 again and see what happens. May work, may not work, but give it a shot. And what's your next step? Skip a line, draw a line. Then you bring down the 1. And you get negative 1. And here's Chris. Okay? And then you and what do you get? Negative 3. Then you get 3. And then you get 6. Then you get negative 6. And then you get, okay, yeah, you did it right, but it's not a 0, is it? You need that to be a 0 for negative 1 to be another 0 of the function. So therefore, -1 won't work again, but it was worth a shot. Okay? So let's erase the -1. Let's erase all our multiplications and additions. Okay? Everybody see why that wouldn't work?
So -1 is an answer.
That is a 0. We got a 0. And what we're checking to see if it was if you had multiplicity of -1. X equal -1, x equal -1. You could have had up to 4 -1s. Not going to happen here, but yeah, you could have. So that's why you checked it again. So now that we've eliminated -1 from the second one, where do you want to go next? 2. Okay, let's try 2. Okay, and what you do next? I couldn't hear. And what you get? 2, and then 4. Oh, wait, sorry. And what you get? Really? 0. Okay. And then you get, okay, and then you get, then you get, and what did that give you? 0. Ding, ding, ding. We have another winner. Okay. So x equal -1 is a 0. X equal 2 is a 0. Okay. Now, time out, folks. What does this represent? Okay, what degree polynomial? Say again? No, not quite. You started with a 4th, and that had 5 terms. Then you went to a 3rd, and that was a 4 terms. So this makes a square with 3 terms. And what do we call a square polynomial whose maximum degree is 2? Quadratic. And what can you do with a quadratic? Yeah, you can either factor it or use the quadratic formula or any other technique, but we have techniques for that. So stop here and just rewrite this as your quotient of those 2 factorizations. And what do you get? X squared plus 3. Set that equal to 0, and guess what? There's not any real zeros that will make x squared plus 3 equal 0. There's 2 imaginary, yeah, if x is equal to plus or minus the square root of 3i. That's the only thing that's going to work, okay? And it says find all the rational zeros, those are them. But these are complex zeros, no more. Only had 2. Remember, we were up to 4, but we didn't have to have 4. Okay. Now here's another thing to notice here. When you do have complex zeros with imaginary parts, then they're always going to come in pairs. Okay. And you will see it, right? Okay. Anyone else come in since the called roll? Okay. All right. So there are only 2 rational zeros, but at this point, you found out the last 2 are complex with imaginary components. That's all you have to do. Is there a question?
I was just trying to get that.
Okay. You get it from here.
Okay. I thought you were going to use that.
Okay. You see, you started out with a function of x, and you only use the coefficients, right? And then when you divide it, you had another coefficient of x, function of x with different coefficients. You drop by 1 because you're dividing by x equal -1, x equal 2. So you drop by 1. So this now represents x cubed, x squared, x to the first, and constant. Okay? Then when you divide again, it drops down to x squared, x constant. So x squared plus 0x plus 3. That's equals 0. You're finding the rational zeros. No more rational zeros. They're all complex with imaginary parts to them. Okay? So you did it. You found the 2, but I mentioned this before, I'll say it again. Whenever you have complex with imaginary, as long as you had integral coefficients, or even just real coefficients, that's going to always round up. If you do have any complex with imaginary parts, they're always going to wind up in pairs, and they're going to be conjugate pairs of each other. Plus I root 3 minus I root 3. But we're not messing with those. They ask for rational zeros. There they are, the only two. All right? That's how we did it. You want to watch how they did it? See if there's any difference. Let me erase what we did. Any questions before I erase it? Okay. All right, first thing they do, because the leading coefficient is 1, all the possible rational zeros are, just like we said, the rational factors, the factors of your constant term. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. That's all the possibilities. So let's start with the plus 1. Well, they didn't do that, did they? They just went straight to the ones that they knew were the answers. We worked our way there, and we got there pretty quickly, too. We checked and saw that plus 1 didn't work, so then we went to minus 1. When we did a minus 1 once, we found a 0, so therefore that was a 0. X equals minus 1 is 0. Then we tried minus 1 again. It didn't work, so we went to the next one. Y'all chose 2. Good choice, because when you did that, you got to another 0. So x equals 2 is a 0. When you get down to 3 here, okay, 3 that's not 0, stop, because this represents a quadratic. Fill in the variable, and then see if you can factor it. If you can't factor it, use the quadratic formula. Can't, well, you'll be able to get some answer there. If these come out factorable or rational zeros to it when you use quadratic formula, then you got 2 more rational zeros. But if they come out irrational, there aren't any more rational zeros. Or if they come out complex with imaginary parts, then there's certainly not any more rational zeros. So that's all we got. The bottom represents the F factors into. Now here's the other thing. I was going to say this. They beat me to it. If x is equal to 1, what is the factor that corresponds to that? Add 1 to both sides. X plus 1 equals 0. So, therefore, that's the factor. X plus 1. And Monica's here. Okay. All right, has anyone else come in since the public? Okay. And if x equals 2 is a 0, what's this factor? Again? X is minus 2. You have to subtract 2 from both sides. X equal 2 is a 0. X minus 2 is the factor. And then this one is a factor as well. This one's not factorable in the real number system. Certainly not factorable in the rational number system. Can't do it. So not only did you find your 2 rational zeros, you also found the factorization of that polynomial, which I couldn't do. Okay? I could not factor a 4th degree polynomial without doing this technique. And here we've done it. Make sense? All right. They jump to example. Wait a minute. You let me mess up. Okay? They skipped example 2. We need to do example 2. Find, if possible, the rational zeros of f of x is equal to x cubed plus x plus 1. Okay? Now, what do you think the possible rational zeros would be? Plus or minus 1, that's all you got. It's the constant term divided by the leading coefficient. This is plus or minus 1, that one's plus or minus 1. That's all you got, plus or minus 1. And plus 1 is real easy to do, right? Okay, let's just plug in plus 1. What does this give you? Plus is 3, that's not 0. So plus 1 is not going to work. So let's do -1 and see if it will work. Okay? And what do we put inside the house? Did I hear 1? 1. Why is it not a 1? 0, because you're missing the x squared term. You have to account for every power. Okay, next. 1 and next 1. Perfect. Okay, then you do what? Oh, I always count. 4, 3 plus 1, 4. Yes, we got the right number of terms. Okay, then skip a line, draw a line. Okay, and bring down the 1. And then, and you get -1, then you, and you get, and then you, and you get, and then you, and you get 2, right? Then you, and you get, and then sadly you get not a 0. So that means there are no rational zeros for that polynomial. You know there's got to be one. How do you know there's got to be a 0 for that polynomial? Yeah. It has something to do with that 3 right there. And it has something to do with your end behavior. Say again? It has to cross. Because when x is very large negatively, that's going downhill. And when it gets very large positively, it's going way up there. Okay? So guess what? It's a polynomial. It's smooth and continuous. Got to cross the x-axis somewhere. But it's not going to be at a rational number. It's going to be at an irrational number. Because complex numbers don't cross the x-axis. Okay? But the irrational number would. So that one has no rational 0 between, well, it has no rational zeros at all. And let's not even get into trying to find the irrational zeros. Now, by the way, I thought they would already show this, but they haven't. There is a little blurb on this page, 153, about a French mathematician, Jean-Laurent D'Alembert, I guess is how you say it, worked independently of Carl Friedrich Gauss, trying to prove the fundamental theorem of algebra. His efforts were such that in France, the fundamental theorem of algebra is frequently known as D'Alembert's theorem rather than Gauss's. Okay, but they did work independently of each other. Another one of those cases, you wound up with two people going after the same thing and both achieving it independently. All right. Example 3, I think we finished with then. Are they going to show the graph or not? Let me see. Yeah, there's the graph. Okay? We found the 2 rational zeros. They were at -1 and +2. Okay? And guess what? The other 2 were irrational. They were complex. So therefore, they're not going to cross the x-axis. Irrational zeros will cross the x-axis. Complex will not. Okay? So therefore, this is what that function looks like. Again, that's an even coefficient, maximum coefficient, even leading exponent, 3, but positive coefficient, so it's on the up and up. So it's going up here, here, so it has to have a minimum somewhere down there. And we're not messing with that. All we're looking for is the zeros. Okay. And we know the other 2 are complex with imaginary parts. All right, any question on example 3? Okay. Now, bottom of page 154. When this leading coefficient of a polynomial is not 1, then the list of possible rational zeros can increase dramatically. Okay? In such cases, the search can be shortened in several ways. Okay, we'll get to that in a minute. that increase is going to come from fractional forms, no longer all integers. But there still may be some more integers, I think, but there would be quite a few fractions. Okay? Now here's how they say that can be shortened. Programmable calculator can be used to speed up the calculations. Yeah, but if you have a good enough calculator, you can find your zeros without even doing any of this. Okay? A graph drawn either by hand or with a graphing utility can give you a good estimate of the location of the zeros. Yeah, but if you had that, you wouldn't need to look for them. Okay? You could find them otherwise. The intermediate value theorem, along with a table generated by a graphing utility, so all this is depending on having fancy calculators, okay, can give approximations of zeros, okay? So yeah, these work. Are there a couple more? It looks like there should be at least one because they have a semicolon there. Yeah, here's one more. Synthetic division can be used to test the possible rational zeros. Yes, that's what we've been doing, and that's really quick and easy. Finding that first zero is often the most difficult part, okay? After that, the search is simplified by working with the lower degree polynomial attained by synthetic division. Every time you do synthetic division, get a zero remainder, then you have another factor, okay? So you use the simple one. Recall that if x equal a, and this is what we're doing before, if x equal a is a zero, then x equal a is also a solution, and what I thought they were going to say, x minus a is a factor. Remember that. If x equal a is a zero of the polynomial function, if the remainder is zero for your synthetic division, then x equal a is a solution of that, f of x equals 0, and x minus a is a factor of that polynomial f of x. Remember, those are all equivalent. All right, now they're jumping to conjugate pairs without doing example 4 or 5. So let's go back and do example 4. Okay, let's erase what we got here. And by the way, you don't realize this, but Screencast-O-Matic and the pen or computer, something is doing much better today. Yesterday, if I got the pen close to the screen, it started writing whatever little squiggle it wanted to write. Today, it's not doing that, knock on wood. Let's hope it doesn't start. All right, and by the way, let me also say this. Every example in the book is followed by a checkpoint. The checkpoints have audio-video solutions at LarsonPrecalculus.com. Take advantage of them. Do them as soon after class as you can. All right, so let's do example 4. Find the rational zeros of this function. F of x equal to, get out of there, okay, 2x cubed plus 3x squared minus 8x plus 3. All right, where do we begin? Where do we begin? Where do we begin? Okay, leading coefficient is, whoops, I looked at the wrong one, 2, okay? Okay, so that's going to tell us something. What else do we need to identify? The constant term, that's a 3. Okay, we got them identified. What do we do with them? Okay, we're going to ultimately factor them, but what we're looking for are the rational zeros. So if they're rational zeros, they got to be a rational number of the order P over Q. That's what it means to be a rational number, something over something. What are those possible P's? And this is what you were mentioning. Yes, these are the possible rational factors, the factors of 3. That's plus or minus 1 and plus or minus 3. Okay? How about for the denominator Q? Plus or minus 1 and plus or minus 2. Perfect. Okay, now let's list out what they could be, all the possibility. Now, I don't do it the same way the book does. I'm going to show you the way I do it. I like to start with the integers, and then we'll go to the fractions. I know y'all love your fractions, but I like the integers a little bit better. That's plus or minus 1 and plus or minus 3. How do you get that? Just put those two over plus or minus 1, and you got the integers. Now do them over plus or minus 2. And now you pick up a few fractions. So what do you get when you put plus or minus 1 over plus or minus 2? Plus or minus 1/2. And when you put plus or minus 3 over plus or minus 2, what do you get? Plus or minus 3/2. Okay, so we're down to 4. Not much worse off than we were before, except some of them are fractions. Okay? Now, what do we do next? Where would you begin? Of all those. I know some of you want to go right to negative 3/2, right? No, not yet. Let's see what we can get. Oh, I got to pick up drawing. What's the easiest one to check? 1. Because all you have to do is plug in your coefficients. Let's add them. 2 plus 3 minus 8 minus 3 plus 3. 0. You just found your 0 without having to do any thing else. You just plugged in the plus 1. Okay? Now notice, yeah, if you plug in plus 1, 1 cubed is 1, 1 squared is 1, 1 is 1. You just add your coefficients. And they happen to add to 0, so you really don't have to do anything. Well, you do. So let me not get too carried away. CJ is here. We got 3 in a row in one spot of the alphabet. That's good to see, finally. Anyone else come in since the called roll? Okay. Now, we know that x equal 1 is a 0. We still got to do our synthetic division because you got to come up with the other factor. So we'll put the 1 on the outside, and what goes on the inside? 2, 3, negative 8, and 3. Do we have enough numbers there? Our degree is 3. We got 4 numbers. Perfect. Okay? Then you do what? Skip a line, draw a line. And then what? Bring down the 2. What next? Multiply, and that gives you 2. Then you, and that gives you 5. Then you, that gives you, then you, that gives you, then you, and that gives you, and 0. Yes, we knew that was coming. We had already checked it. But what do we have now we didn't have before? The quotient. And what does that quotient represent? 2x squared plus 5x minus 3. And guess what we're going to try to do? Factor it. Good. Okay. Don't know if we can, but let's give it a shot. If we can, we're going to find our other 2 rational zeros if they exist. Okay. Now, what's the only possible factorization for 2x squared? Okay. That's, yeah, x and 2x. Okay. Have to have the x in there. So that would be x and 2x. Okay. Now, where do we go and look next? The sign of the last term. What is it? Negative. Which means, what about these two signs? One's plus and one's minus. Let's just arbitrarily put it plus minus. We don't know if this is right. This is trial and error. Now, what's the only possible factorization of 3? 1 and 3. Well, let's put those in that order too. 1 and 3. Okay? Now, okay, we'll see. Let's check and see if we factored right. No guarantee, we're just choosing. Okay? X times 2x is 2x squared. Yep, that one works. X times minus 3 is negative 3x Plus 2x would be negative x. Wrong answer. We got a plus 5x. So therefore, since the number's wrong, change your numbers. So that means we're going to move the 3 over here and the 1 over there, if I can get it to erase. So we'll put 3 here and 1 there. Now let's see if it works. X times 2x is 2x, right? Yeah, we knew that worked. And now we have our outers are negative x, innards are plus 6x, minus x plus 6x is plus 5x, ding, 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 and then we have the last 3 times negative 1 is negative 3. Yes, 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 we have the correct factorization. But they weren't asking for factorization, they're asking for rational zeros. So now we go the other way. What would be the zeros for those two? What would be your next step? Since you have the product of these two entities equals 0, you know that. What do you do? Only way you can have product of two things equaling 0, what has to be true about one of these two things? It has to be 0. What other numbers can multiply together and give you 0 answer? Nothing. Only 0. So you set each one of those equal to 0, right? Let's do the first one. What would that give you? X plus 3 equals 0. Subtract 3 from both sides, and that gives you x equal minus 3. And sure was enough, that was one of our possibilities, wasn't it? Okay, what's the other one? Or 2x minus 1 equals 0, and what would that result in? Add 1 to both sides, and that gives you 2x, is add to 0, is equal to 1. Divide by 2, and that gives you x equal 1/2. Ha! There's the other one. X equals positive 1/2. Yeah, we guessed right. Okay. We got 1, 0 from x equal 1. Another 0, x equal negative 3. And the third one, x equal 1/2. So we found our 3 zeros. I didn't write down the first one. X equal 1 was the first one. Well, we'll get out of there. Okay. So here's 1, there's 1, there's 1. What's the most you could have? 3. And we found all 3. That means there are no irrational zeros and no complex zeros. They're all rational zeros. See, 1/2 is a rational number, not an integer, but the negative 3 and 1 are actually integers. Remember, for this to work, the coefficients have to all be integers. They can't be rational for the rational zero test to work. But the zeros could be rational. Does that make sense? Okay, now this wasn't in the book. I mean, it wasn't on the slide set, is in the book. Let's see if the book got it right. Oh, look at that. X equal 1, x equal 1/2, and x equal negative 3. Good for them. There's another checkpoint there, middle of page 155. Do that as soon as you can. Okay? How about example 5? All right, to erase this because it's not going to show up on the slide set. Okay, to erase? Okay. So we'll erase all that ink. Now let's do example 5. Find all the real zeros of negative 10 x cubed. I can't write. I say one thing and write something else. Okay. X cubed plus 15x squared plus 16x minus 12 equals 0. Okay? Now, this isn't mentioning a function at all. It's saying find all the real zeros. Okay? How would you find all the real zeros? Okay? Well, one thing you certainly can do, you could try factoring if you wanted to. This one does have 4 terms. You could try factoring by grouping. I just don't think it's going to work for you. Okay? Because this will have a minus 5x squared out of the first one. And that leaves you with 2x plus minus 3. And on that one, you can factor out a 4, and you have 4x minus 3. So that's not going to work for you. So factoring by grouping won't help any. So what might we try next? Guess right. Solving a quadratic function is the same as finding the zeros for a quadratic function. Okay? Now, before I start doing, well, we don't even need to. Let's treat that as a quadratic function. What would be your possible zeros? Oh my. What would they be? Rational zeros would be something in the order of p over q, where p is what? All the possible factors of your constant term 12. Tell me what they would be. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. Oh, we have enough to look at? Hey, but we haven't even gotten to our denominator yet. What's the possible factors of your denominator? Plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. Okay, now they say we're supposed to list all these. I really don't want to, but let's do, because they told us to. So what would this result in? I like to go for the integers first. Everything in the numerator over your first term. And that's just plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus, get out of there, 12. Okay? That's all the ones without fractions. Let's start the ones with fractions. What's your first one? All the numerators over your second denominator, which is plus or minus, get out of there, 1 over 2, right? 1/2. What's your next one? 1 over 5, plus or minus 1/5. And your last one, plus or minus 1/10. Okay, so there's a few more, but we still have another denominator, so all these over your third. Wait, I'm sorry. I messed that up. Let me start over. Okay, those are right, but what I meant to do was like we did before. Okay, sorry. I'm sorry, I got messed up. I mean, that's perfectly okay to do it that way, but we didn't start out doing it that way. Let's do all the numerators over the 2. So you got plus or minus 1 over 2, that's 1/2. Plus or minus 2 over 2 is going to be what? 1. We've already got 1. Don't do it again. Okay? Then we have plus or minus 3 over 2. Okay, we don't have that one down there. And then we have plus or minus 4 over 2. We already got that one. That's 2. And plus or minus 6 over 2. Well, that's 3. We already got that one. And plus or minus 12 over 2. That's 6. We've already got that one. So you see, that wasn't nearly as bad as what we thought it was going to be. Okay? But let's go to the third denominator. And that's where we get into plus or minus 1 over 5, and the next one would be plus or minus 2 over 5. This one's not going to be all that short. Next one's going to be plus or minus 3 over 5. And the next one's going to be plus or minus 4 over 5. And the next one's going to be plus or minus 6 over 5. And then we have a plus or minus 12 over 5. Wow, I had every one of those. But then let's go to the last denominator, and that's going to be, the first one's going to be plus or minus plus or minus 1 over 10. The second one's going to be plus or minus 2 over 10. But what's 2 over 10? 1 over 5. We already got that one, so you don't have to write that one down. The next one's going to be plus or minus 3 over 10. We don't have that one, so plus or minus 3 over 10. And the next one is plus or minus 4 over 10, but guess what? That's 2 over 5. We already got that one. Next one's plus or minus 6 over 10, but that's 3 over 5. We already got that one. The next one is plus or minus 12 over 10, which is 6 over 5. We've already got that. So, I don't know about you, but I hope we're not going to have to do all those. Okay? All right. So let's start. What's the easy one? The easiest one to do. 1. No! Don't go start with fractions. 1's the easiest. And how can we do 1? What makes it so easy? Just add the coefficients. So let's do that. Minus 10. That'll be plus 5. Plus 21. Okay. Our luck ran out. 1 doesn't work. Which one you want to try next? I think he wants to go for 1/5 or something like that. No, let's not. Let's try negative 1. It's going to be relatively easy. Because we know that plus 1 isn't going to work. Okay? Let's try negative 1. Put negative 1 outside the house. What goes inside the house? Negative 10. Whoop, I put a comma. I don't need a comma. Okay, 15. Wait a minute. Let me get my pen back. 15, 16, 12. Okay. And skip a line, draw a line. Oh, it's negative 12. You're right. Okay. And? Second? Negative 10. Bring that down. Second? Multiply what you get? 10. Second? And what you get? 25. This isn't looking good, is it? Oh, this may not be too bad. Next. And what you get? Negative 25. And then you? And that gives you? Negative 9. Not going to work, is it? Next you'll get positive 9. That's not going to add to 0. So negative 1 didn't work either. Sorry about that. Okay? So we're going to erase the negative 1. We'll erase our multiplications and additions. But we'll leave that negative 10 because we're going to have to bring that down again anyway. All right. What you want to try next? So minus 1 didn't work either. Okay? What you want to try next? 2. Let's try 2. All right. I already brought down the negative 10. What does that give you? Negative 20. And then, and what you get? Negative 5. And what you get? Say again? Really? 2 times negative 5? Negative 10. And then? And you get 6. Didn't you? And what'd you get? 12. And what'd you get? 0. Ding, ding, ding. Hey, we found a 0. X equal 2. That's a rational 0, so x equal 2. Okay, now what's the good news? We're left with a quadratic. What can we do with quadratics? Either factor or use quadratic formula. So we don't need to try anymore. All those that we did, we eliminated 2, found on the third try one of the zeros, and now we don't even need to mess with them. Well, we'll use them, but let's see what we got. Okay? So what does that represent, those 3 terms? Minus 10 x squared minus 5x, a little louder, plus 6 is equal to 0. Okay, what you want to try? Want to try factoring? Let's do. Can't dance, okay? All right, what is one possible factorization for negative 10x squared? Okay, 2 and 5, okay? Now, you know what I want to do? And it's okay to do because that is an equation. I want to multiply that equation by minus 1. The whole equation, both sides. And that would make a plus, and a minus. You know, I like working with leading positive coefficients better. If it was a factor of the other one, it's going to be a factor of this one too. Okay? So let's see what we get. Okay? So this time it won't be plus or minus. Let's do 5 and 2, 5x and 2x, right? And then where do we look next? Sign of the last term, and what does that tell you about these 2 signs? One's positive, one's negative. We'll put them in that order since you said it that way. And then what will we look for next? Possible factors of 6. What would they be? 2 and 3. I'll write them down the way you said them. Okay? Now, I think that's not a bad choice. Now, here's why I say that. If you had said 3 and 2, I would have said bad choice, because that would have indicated 2 would be a factor of this. If 2 is a factor of that, it would have been a factor here. It's not. So that's a good choice here. I don't know if it works, but it's a good choice. Let's see if it does. Let's pull it. 5x times 2x is 10x squared, right? That checks. All right. Next, the outwards, minus 15x, and the innards are plus 4x, and then the last are minus 6. Okay? I know that works, but SpaghettiOs. Minus 15x plus 4x would be minus 11x, and we got a plus 5x. So that doesn't look good. Our numbers are wrong. So, what's that? Okay, we want to swap numbers, but guess what? We can swap 2 of these numbers. Let's swap the 5 and the 2x. Let's swap those. Okay, we'll make this 2x. Nah, that's still not going to work. I don't think this is going to factor. Well, we could try other factors like 10 and 1 and stuff. You know what I'm real tempted to do here, because we're running out of time? Let's use a good old quadratic formula. That might be easier than trying to do all our trial and error. So what does the quadratic formula tell us? X is equal to, get out of there. How does quadratic formula go? Anyone remember? Nobody remembers. How sad. All that time you spent in Math 100, And you've forgotten it all. Huh? Okay, well, it has that in there. It starts with minus b, which in this case will be minus 5, plus or minus, you got that part right, followed by a big square root, and that would be b squared, which is 25. I'm doing it fast because we're running out of time. 25 with the pen slow, okay? Always minus 4 times AC, and AC here is 10 times 6, 10 times a negative 6, so times 10 times a negative 6, okay? And we're going to divide that by 2a, which is 2 times 10. All right. Yuck. Okay. This is going to be minus 5 plus or minus the square root of 25. Now, what I do next is count my number of minus signs. The minus 4 is always a minus. And you count the other, you got one more. So 1 and 1 is 2. 2 minuses make a plus. So that's going to be a plus. That means it's not going to be complex. Okay? Plus, and then when you multiply those two things together, you get 240. Right? 4 times 6 is 24. Times 10 is 240. Divided by 20. This is looking bad, folks. Okay? All right. This will be a minus 5 plus or minus the square root of, that would be 265 over 20. And if any of you have a calculator, get on it real quickly and see what the square root of 265 is. If that comes up being an integer, that means we could have factored, but we'll tell us what the factor is. Is that a perfect square? 265, square root of 265? I think not. Any of you get it? Square root of 265? What do you get? These calculators are slow. Okay, as soon as you got a point, blah, blah, blah. Nope. That is your answer. Now, you might be able to simplify it a little bit. For instance, see if you get a 4 out of 5 here. And that would leave you 5 going to 26 5 times 3, so 53. But you know that's not going to happen either. 53 hasn't got any other purpose. There is your answer. The next x is x equals minus 5 plus the square root of 265 over 20. And the next one is x minus x equals minus 5 minus the square root of 265 over 20. Neither one of those are rational zeros. Those are irrational zeros. So the only rational zero you have is that. And that, sure enough, I think is what the book got, right? It says, oh, no. It said find all the real zeros. So the next one is x equal minus 5 plus the square root of 265 over 20. And the other one is x equal minus 5 minus the square root of 265 over 20. Guess what? Those are real zeros. They're not rational zeros. And they, I hope I didn't mess something up there. If you plug those in, I think you see, I hope you see, yeah, it comes out the same two numbers that they got in the book. Okay, let's stop there. We're going to start with conjugate pairs next time, which we're not going to do a lot on. We're going to go through that pretty quickly. Let me give you some homework exercises. Homework exercises will be any of the odds 9 through 13. 9 is all of them are at Calc Chat. 9's at Calc View. Do either 15 or 17. They're both at Calc Chat. Do any of the odds 19 to 27. They're all at Calc Chat. 25's at Calc View. And try either 29 or 31. They're both at Calc Chat. 29's at Calc View. And I think you can do either 33 or 35. They're both at Calc Chat, not at Calc View. Believe you can do 37 or 39. They're both a calc chat, none are a calc view. Now, stop there. We'll pick up the rest of those later.
I was wondering for this slot, like, if we want to transfer somewhere else, will I get an associate's here, or will it just, how does it
You
work?
can get associates here in psychology, yeah.
And then transfer, I can still
Yeah,
transfer somewhere
right.
else? Okay. Well, I can just plan on doing that. I just didn't know which
Okay.
I needed to,
Do you need me to sign this?
please.
Okay.
And then just,
Am I your advisor?
you are.
Okay, great. Okay, they'll probably change advisors. I'm going to guess it'll be Miss
Miss Howard?
Huh?
Miss Howard?
Howard, is who I guess. I couldn't think of her last name before either. Okay, and today's date is the 10th, is that right?
The
Huh?
17th.
17th, that's right.
Mr. Fowler, when is the test going to be?
Okay, that was a question, and the person left before I got to answer it. Okay. All right. You take it.
Okay, which one do I need?
It's AA, but they'll know that. You know, if you want to check it, you can. Okay. The answer on the test. Okay. I'm getting the quizzes in now. We've got to finish 2.5, which is we're fairly close to finishing it because we're not going to do all the things on conjugate pairs. I've already mentioned those. Then we got to do 2.6, and that is a moderately long section, but we're not going to do it all, okay? So I'm guessing it won't be before next week, probably the following week, which is going to get us awfully close to the final. The final will be, I think, the Tuesday of final week. Well, we may have another quiz in there, too, if we get a little bit done in Chapter 3. Yeah. All right, glad to.